I see that the number of participants is rather steady. So, and as the registration link says 9:30 or 10:30 in Latvia, I suggest we start. Welcome everyone to this highlighting organic chemistry in Latvia. It's part of a webinar organized by the Division of Organic Chemistry of EuChemS. My name is Adriaan Minnaert and I'm chairing the division. Every quarter we highlight organic chemistry in a European country. And these webinars are also recorded. So if you want to look back a certain highlight or you missed one, you can always find those back either on the EuChemS website, look for Division of Organic Chemistry and highlighting, or you go to YouTube and you look for something like EuChemS Organic Chemistry or EuChemS Organic Chemistry highlighting. Then you will find all the previous versions. So the previous one was the Netherlands, the next one is Belgium, and today we have Latvia, and my colleague Maris Turks has been so kind to compose a nice program of 6 speakers. The contributions are 30 minutes, including some questions and answers. So if you have a question for the participants, please put them in the chat box, so the Q&A box that you find below at the bottom of your screen. I will read out these questions and so that the speaker can answer them. You don't have access to the mic, so you have to do it via the Q&A box, but normally that works fine. Yeah, without further ado, I would like to introduce Professor Maris Turks from Riga Technical University, who will give the first presentation. Maris, the floor is yours.
Yeah, thank you, everybody, and hello. It's nice to see you in this virtual mode. And indeed, today we present some mosaic of organic chemistry in Latvia. So for those who don't know, that's how we look on the map. And I just will give a few slides of the introduction of also some historical points and then proceed to my contemporary scientific presentation. Yeah, so in Latvia, we have chemistry in several places. But if we do exactly zoom in where the organic chemistry in some kind of ways are possible, then definitely the main place is capital Riga, where are 2 major science universities, University of Latvia and Riga Technical University. And there is organic chemistry in those. And we have also, like other European countries, has this independent institute system. So we have Latvian Institute for Organic Synthesis, who is also today very strongly represented. And for sure, some organic chemistry is also an Institute of Wood Chemistry. Besides that, some smaller divisions like food chemistry, which is also organic, as we know. It's in Latvian University of Life Science and Technologies in a town which is like 50 kilometers from Riga in Jelgava. And then closer on east, we have another university, local one, Daugavpils University, where is also some department of organic chemistry and some synthesis is going on. So that's a very broad overview. And just to put some few points how we came to today. So it was Riga Polytechnicum, which was founded in 1862. Back in time, actually, it was made by similarity of ETH in Zurich, which is some couple of tens years older, something like 20 or 30 years older than Riga Polytechnicum. And at that time, the Riga city saw that this technical education and natural science education needed. And so that from this famous past, let's say, we have Paul Walden, who was professor in Riga Polytechnicum and is known for several things, but those closer to organic chemistry, it's Walden inversion, so SN2 chemistry with its stereo inversion, which was published in 1896. But Walden is known also for liquid ionic liquids, which we also actually will have a talk today. Then over the years passing, we have another chemist, Ojārs Neilands, who has done many things. In his active period was in Soviet time. There was this Iron Curtain, but anyhow, so he's the first who synthesized this particular iodine 3 compound, which is very, very known and nowadays actually bears another name, but Ojārs Neilands was the first who got it, and he was also active in organic materials, especially those which are electroconductive and light-emitting materials. And also is author of a teaching book for organic chemistry in Latvian, and which was also later actually broadly available in whole Soviet Union and translated in Russian. And then we pass on another piece of mosaic is Edmunds Lukevits, who was longtime director of Institute of Organic Synthesis, and he is known for organometalloids, particularly silicon and germanium chemistry, and despite the Iron Curtain, actually was known also in West, and has several papers, many papers actually on this chemistry also in those journals which are available outside of former Soviet Union. And if we are closer to nowadays, we should mention Ivar Skalviņš, who is the father of meldonium, so leading this medchem group. And meldonium is a cardioprotective drug, cardiovascular agent, which is registered in eastern part of Europe, but for broader society, I guess, was known since doping scandals in sports. The first was tennis player Kurnikova, who was Sharapova, I'm sorry. Yeah, that was Sharapova, who was came in close discussion with this. But otherwise, it's really a cardioprotective drug which is legally used. So that's very short how we look, where we came from and what is going on. And indeed, today then we made up this program by representing two science universities, Riga Technical University and University of Latvia, where the organic chemistry is done, and then Latvian Institute of Organic Synthesis. And also, we try to do like two full professors, two associate professors, and two young investigators who are in the beginning of their career, just to see also this continuity. Okay, with this said, I then proceed to the scientific part, and my presentation will be on metalloid shift, mostly on 1,2 silicon shift, but also some germanium will sneak in at the end. So my group in general does several things. Besides organosilicon chemistry, we do also Birch-bark terpenoids. We are also active in heterocyclic chemistry, particularly with nitrogen-rich heterocycles, both from chemical point of view and recently also in energetic materials when nitrogen rich compounds blow up in controlled manner. Some also organic chemistry with sulfur dioxide and also some industrial contracts. But today's topic is metalloids, silicon, a little bit of germanium. And so I wanted to start with reminders that there is this phenomenon called beta silicon effect, which is hyperconjugation stabilized beta silicon carbenium ions. And there are two ways of this stabilization. Most likely the mostly known is vertical stabilization, which is more or less the same as hyperconjugation of nearby standing CC bond to carbenium ion. But there is also so-called non-vertical stabilization, which is then more known for metalloids, where actually three-member cycle in at least as active species can be formed. And if you look at stabilization effects, what it does, so if we reference allyl cation as we know due to resonance effect stabilization, then we see that beta silicon effect is especially for the secondary carbenium ions, more or less on the same level. So it's, let's say, significant stabilization. And for primary carbenium ions, which are very difficult or sometimes even not possible to form at all, without stabilization, then for sure the stabilization actually gives even more impact. Whereas if we go already for quaternary centers, which are then ionized, then for sure there is so much of other hyperconjugations that beta silicon effect is not as pronounced. And if we then go further to vinyl cations, then due to geometry problems, because then the overlap is not as good anymore, then this over stabilization effect is slowly vanishing, but not completely, and that will be the discussion of today. And especially if we look this non-vertical stabilization, where the three-member transition state at least is involved, then finally it can follow with a full migration. The same as we know for Wagner-Merwein shift in carbon compounds. And if it is this carbenium ion coming from sp3 systems and it has really nicely aligned p orbitals, then it's easy. Whereas if we have this vinyl cation, then neither the stabilization nor other things are as straightforward. But if we arrange the system in a way that after migration we form a decent allylic cation, then actually we can make these things happen, so that stabilization of vinyl ion is still sufficient with silicon, that it can facilitate afterwards this migration. So, and this will be the talk of today, how we use this particular mechanistic concept to develop some new methodology. We are definitely not the first who came in. Some of these things were known already before. For sure, most of silicon chemistry, which is dealing with propergyl and allyl silenes, is definitely Kasome-Sakurai type reaction, where there is no time for other migrations, where the silicon gets chopped off. And if you start with propergyl silenes, you get alanyl products. Nevertheless, there are some few examples. When you come in with, let's say, well-adjusted electrophile-nucleophile pairs, then the electrophile activates the carbon triple bond by adding. Shift happens, and if I put my pointer, so here it's an activated system, then actually silicon can shift, and those which were early examples, those few, then electrophile is directly attached to the nucleophilic part, which becomes nucleophilic afterwards, and then closes the cycle. And mostly those were like CC and O and CO systems, which are shown here. The only example that we have found before in literature which uses electrophile, which doesn't bear a nucleophilic part, which will afterwards add. It is published by Ferreira. So we activate either with carbophilic Lewis acids or with electrophiles shown here. And then the system is built that, again, shift can happen. Plus, there is, let's say, finishing with something like pinnacle mechanism. So the activated alcohol becomes a carbonyl group by logic arrow pushing. So with this things known, so we started to think what we can do and why it is important. It's important because in this way, both allyl silenes, but particularly also propergyl silenes, can become as important tools for 1,3 difunctionalization, which by no means is so developed as 1,2 or 1,4 difunctionalization in chemistry. So for sure we have some examples especially those which deal with CH activation, where that you have directing group, which directs the um, CX bond formation in distance 1, 3. We have also chemistry by cyclopropane ring opening, and for sure we have allylic oxidations and other allylic transformations by transition metal catalysts. But that's, let's say, in broad view, the most developed. So other methods could be useful. And so here we are with all what was said, then we designed the process in the way that we activate propyl with electrophile. We let the silicon migrate in 1-2 migration process. The formed allylic cation is okay because it's allylic, plus there is some still tiny, let's say, stabilization also for beta silicon effect, even if the orbitals are not in the very good way. And this cation, then we can trap now with nucleophiles, so we don't let silicon to eliminate, and we can do it either in intramolecular fashion if we have built in R2 group some nucleophilic species, or finally, what is even more important, we can do nucleophile addition, which is separate nucleophile. And then in that way, we can see, particularly in this, that there is indeed 1,3 difunctionalization, but all other possibilities are okay. Yeah, sometimes if we build also some nucleophilic part in the system in here, then we can also close cycles on another time. So we will see how it can function. We came into this chemistry, should be honest, let's say, by some side products. That was in the beginning not intended research. So we were dealing with propyl chemistry, what we wanted to do with sulfur dioxide, etc. And we suddenly saw that in the presence of strong acids, there is interesting isomerization. And if we think about mechanism, so it's exactly what's shown before. So proton activates the system, silicon is shifting, and then the cation, in the absence of any reasonable nucleophile, gets that cation eliminates proton, and we get a dyne system. So that was let's say, even if the nucleophile is not added, it was proof of the concept that this system works, and we published a paper on this isomerization process for synthetically useful silicon substituted dienes. It is interesting that this process can be influenced by solvent, because if we, as in previous slide, if we do it in halogenated solvents with, let's say, reasonable polarity but not too big polarity, so we need really strong acids, something like triflic acid or bistriflimide, etc. But if we go to, let's say, more polar systems, and one, for example, is liquid sulfur dioxide, in those systems already we can operate with much weaker protic acids, actually including water in liquid sulfur dioxide, which is actually that equilibrium to sulfurous acid is not as pronounced in liquid sulfur dioxide as solution. So if you have sulfur dioxide in water, there is enough of concentration of acid, but actually water in liquid sulfur dioxide is not so acidic. But anyhow, it works, and also acids like benzoic acid, etc. Plus, we can directly add also sulfur dioxide in heliotropic manner in one pot process. And also these, just we show that it's possible to variate those silyl groups and also some substituents. And if you have the system installed already with some substituents at both sides, there is also decent diastereoselectivity as for every pericyclic reaction. The same approach is also then further proceed if the propyl has aryl substituent which is capable to act as a pi nucleophile. So the generated cation at this particular position then will cyclize with that aryl group, including even such systems which contain electron withdrawing groups as nitro. Yeah, yields on some occasions can slightly drop, but it's mostly actually due to the silicon group, which then partially can also cleave. Whereas if we take a bigger silicon group, then yields are still at very good level. And now we came to other domains. So we designed the starting materials that we can close heterocycles. So in the sense that there is inner nucleophile in the system, which will trap the formed carbenium ion. So again, for example, this proper glycylene is reacting with a proton, silicon migrates, and cation is trapped with hydroxy group. Here the optimization shows that the best system to promote this process is BIST trifluoride. And the best solvents were chlorinated, so either chloroform or dichloromethane, which is later used. And the same also can be done by halogen electrophiles. And here, by experimenting with, for example, with bromonium sources, we found that the best is particular one in the N37, which gives a decent yield. Otherwise, if the system is not adjusted, also the previously discussed deprotonation of carbenium ion is happening. So that's the main side product, which actually on some occasions could be also very useful because we really can introduce in stereo-controlled manner that halogen atom either here or what we aim in the beginning for this product. And with this optimization in hand, so we proceeded to check which kind of electrophiles and also nucleophilic partners we can do. We can do, the named proton and halogens and also selenium plus electrophiles. And we can close it as lactones. We can do it even double nucleophiles. So it's aldehyde, which is attacking and forming oxcarbenium ion, which is trapped then by water. So we can work also in the wet conditions. Also, some oximes are available for closing, and definitely also nitrogen nucleophiles, especially those which are as sulfonamides. But also simple amides work, and also thio systems work. Even here, some yields with electrophiles like coming from the 7th group is more difficult because definitely sulfur is so nucleophilic that those tend to react also with sulfur, not to go to the triple bond. We can also enlarge the cycle, yet there's also some drawbacks that, for example, this particular reaction with 6-member ring closure didn't give us satisfactory diastereoselectivity. But where we don't have to compete for diastereoselectivity, it works reasonably well, and we can make such kind of heterocycles with a vinyl functionalized side chain. There have been also very initial attempts to see whether we can do it in stereoselective manners of asymmetric catalysis. So it is just really like for the mean of scientific seminar to show that there is something moving onto that side, but is still very far away from being as a methodology. But the hope is still open there. So if we build up another pi nucleophilic system in the side chain, so this concept can be used for example, chromane cycle formation. Again, it's no surprise that those which are, let's say, more electron-rich systems work better. And this particular case on this cycle closings and the withdrawing groups are not as good. Nevertheless, in other systems which are, let's say, electronically okay, we can even do the double ring closing at once by this method. And again, in the case we don't do it with simple proton, there could be stereo control, and actually the stereo control is in two ways. So either we start with a protic system and then do electrophilic attack with a halogen. But in this, what is shown here is that actually the halogen atom is already installed, can be installed in this position, and then proton goes again on opposite side to silicon, and that is shown in this slide. So we can get sterically quite congested Z double bonds, where even such big atoms like bromine and silicon are still on the same side because silicon migration is opposite to incoming electrophile, even if it's small proton. And here was just for those who are students in the audience, I wanted to show that actually known method for separation. So we had some practical problems struggling with separation of alanyl side products, which were formed like from 3 to 5%. And just to show these animations, and if you have the silver impregnated silica gel, then definitely these pi systems interact with silver differently, and it was very easy then to separate, whereas in normal silica gels they just both Lu together, but in this particular system then alanyl product is nicely attached to silver and stays more long on the column, and our vinyl silane product is coming out first. There are also some side reactions which we have observed. If we take some, let's say, not a straightforward linkers, but actually this now give us some rise for other ideas and novel methodology development, because now we see that there is a competition which is a nucleophile. So we have nucleophile already over intended aryl system. We have nucleophile also hidden in this linker in the sulfur atom. And at some point, there is also some competition for this allylic cation, which position of it can be attacked. So in either way, we can get all those products. And now that optimization is on the way to see which of the methodologies is better to develop. And but if we go back to, let's say, more resistant linkers like nitrogen, then again, we can close the cycle in exactly the same way. So there is electrophilic activation, silicon migrates, cation is formed, and pi nucleophile is adding in, making these heterocycles. So the proton, halogens, selenium, that's, let's say, straightforward. So we intended also to do something with carbon, formal carbon electrophiles, so it's not so easy to find those. But there is a method. So if we take lambda 3 iodines and activate them with a copper, let's say, so actually we form copper 3 intermediate, and copper 3 is already electrophilic species, which then deliver carbon atom to our triple bond. And is this all system together is still able to induce this, let's say, plus in the system which is formed, is able to induce silicon shift, and we again form carbenium ion, which can be trapped by inner nucleophile. So we see that all kind of variety of aryl groups we can add in this case. Also some heterocycles, also with lower yields. The drawback of this method was that it was not well working with other inner nucleophiles, so the easiest alcohol was that which was possible to do. As we see that with the carboxylates, the acids as such are not good, so we have to actually protect and to make them, let's say, carbenium type of leaving group. So then the carbonyl can attack, and then tert-butyl is chopped off by some other nucleophile to form lacton. In general, it's possible. So far, optimization was not so successful. And in general, it's possible to do also with nitrogen nucleophiles, but also their yields are not the greatest. And also in this case, again, if we variate the length of the linker or the form of where the nucleophile comes, so we can make this system for other nitrogen heterocycles. So we see that then suddenly by changing the lengths and linker, we can start to form six-member heterocycles with aryl substituent, which comes from this copper 3 intermediate. So far we covered everything which is with internal nucleophile. For sure, more fun and more diversity is possible if there is separate electrophile and separate nucleophile. And here we take simple propargyl silenes, activate them by either NBS or NIS, and as we see, nucleophile is either methanol or even acetic acid. And it appears that in these conditions, if we work fast and sufficiently low temperature, which is ambient temperature, then even that acidic conditions are still okay for propargyl silenes. And so we can nicely make allyl ethers with quite activated vinyl, activated but substituted vinyl part. So for acetates already mentioned, but here are the product range. So we can prepare in this way quite highly and stereo-definedly substituted allylic acetates. And also formyl system is possible. So for formyl system, we use wet DMF. So dimethyl formamide is adding, and then water does the last job to actually break it in parts and make the formyl group, which is also a nice method for allyl formate formation. And even simple water does the job. So we can do in acetone water mix with NBS. And so we make allylic alcohols, or we make electrophile nucleophile pair, which contains both in. So for example, simple iodine can add across the propargyl silane system. Very simple. We checked literature whether really nobody has done, and indeed, yeah, that we couldn't find that examples. That so nice and fast functionalization. Product is somewhat unstable because with two iodines and this quite flexible one, it's actually formed in much higher yield, but after isolation, it's only 53%. So we can do also double. Actually, we have seen already double nucleophile addition. Where was that, for example, from aldehyde made acetals, or this when water act intermediate of dimethyl formamide addiction. But now we wanted to meet even more pronounced, so we made a Ritter reaction. And the Ritter reaction definitely has the addition of nitrile, which is quenched by water in very classical way. So that's shown in these examples. But we can do also intentional addition of other, let's say, more pronounced nucleophile, like for example sulfonamides, and then we can make these amidine systems still attached to the allylic position, which is made by silyl migration, and silyl migration is due to electrophilic activation of the system. And this one we can do even with, again, built-in internal nucleophiles. So it's somewhat tricky to adjust the system, but so electrophile is activating triple bond, silicon is migrating, cation is formed. The linker is too short that aryl group cannot do really addition, so it waits for the nitrile addition, and then nitrile intermediate which is activated is reacting with the pi nucleophile. So we are already moving to the end, and so what we can do with these products, definitely we have a system which is useful afterwards for some transition metal catalyzed cross couplings, for example, Suzuki. And we saw that these products now we can make in two ways. So either we activate that terminal triple bond with halogen, do our job, and then make couplings. Or as we saw some minutes ago, so actually we can make a terminal system and directly come in with a let's say carbon electrophile formal synton by copper 3 chemistry. So either way we can get such kind of products, and for sure we can replace silicon. Actually, in this particular case, the direct cross coupling with here Denmark conditions were not as easy. Also, we have some success in that, not published yet, but most straightforward was to replace silicon by halogen and then do some other couplings. And so in this sense, we can see that we quickly arrived to steel beam systems, which are quite important in materials science. And for sure, all others, it's quite busy slide, but all other kind of modifications are possible. So those include, for example, even CH activation if the R group is aryl. So here the palladium 2, which is formed, is doing CH activation in nearby standing aryl group, and we can close the cycle. We can do already mentioned Suzuki, but this time even with allyl acetate. So this allyl acetate, due to the crowdiness here, is not so easy to activate in Tsuji-Trost fashion, but Suzuki reaction happens. These we can proceed to further cyclizations already by ionic mechanism. And again, here we can proceed for silicon iodine exchange and then do other couplings and still have allylic acetate for again further modifications. And closing with germanium. So recently we started also to see is germyl groups doing the same, because about germanium 1,2 migration is really little known. Some examples are there, but like very, let's say, theoretical chemistry. And indeed, in already seen systems, if you replace silyl group with germyl group, it works as well. For example, this particular case, simple, let's say, TBS equivalent of germanium, terz-butyl dimethyl germyl group, activated by proton, shifted, nucleophile attacks, 85% of such vinyl germyl system. And also here, we can activate with already named electrophilic systems and put a halogen atom in stereo-defined way that the double bond is controlled. So if we start from the unsubstituted monosubstituted acetylene, then we have in this position, because again, as mentioned, migration happens anti to the incoming electrophile, and the same is here. So if the halogen is already in the system and activator is proton, then it's again proton is anti to germyl group migration, and then halogen is in syn position there. So with that, I can conclude that already what we have seen, that electrophilic reagents can activate proper silenes, which is known since a long time. But in such design, you can migrate silyl group, and you can do lots of useful things with the formed allyl cation. And all the examples that you can cyclize from this side, from that side, come in with a nucleophile, which is from another reagent, or to come in with nucleophile from another reagent and close with another nucleophile, which is inside. All the possibilities are there. And also germanium here is slowly sneaking in because the chemistry works quite perfectly with germanium, and then other organometallic transformations are more possible if you replace silicon with germanium. So with that said, I should thank my students, group of talented people who have done the work, and thank you for listening.
you, Maris. You will have to live with a virtual applause because the participants cannot make that audible. But at least I see some hands appearing with applause. Thank you very much for this expose. And if people would like to present, okay, there the hands come up. If you would like to pose a question, please go to the Q&A box and then you can type in there your question. I take the opportunity to already pose you a question because you said that, or you showed that if there is an aryl unit in the molecule, it can cyclize, and indeed, if the aryl unit is less electron donating or even electron withdrawing with a nitro group, yields are somewhat lower. On the other hand, I was surprised that you still get acceptable yields even with a nitro group in the phenol. Isn't that surprising? Because normally these are very reluctant in electrophilic aromatic substitution reactions.
Yeah, it depends from which side you come. So if actually, if that for sure, if that nitro or cyano aryl group is on that long linker, which should form, let's say, from the same side where the first cation is formed, then it's for sure more sensitive because then it's like real undependent pi nucleophile. But it's so in proximity in intermolecular reaction, so it does even, let's say, 30% or so that reaction. Whereas actually, if we start with substituted acetylene, which is between aryl group and silicon, which was shown some time ago, some earlier slides, then actually, and we form the indines in that reaction, then one can discuss that is not like Friedel-Crafts type reaction, but actually there is all the orbitals that is more like Nazarov cyclization. And then actually even nitro works quite perfect because then actually it's different type of mechanism
Right. Yeah.
and due to pericyclic transition state.
Okay. Thanks very much. Thanks very much for this clarification. In the meantime, also a question came in from Philip Efnert, who's intrigued by your silver nitrate silica gel column purifications and asks how much silver nitrate do you load on the columns?
Actually, it's quite a bit. It's between 5 and 10% from the mass. But as we work like in contemporary science, let's say in 50 or 100 milligram scales, also the columns are quite small. That method is quite old. It's published many decades ago. It's not that, again, we would not invent it, just that students usually forget such kind of ancient things which exist. And we just pick it up because indeed it's actually used also in natural product chemistry for isolation if it's terpene type compounds which don't have much of heteroatoms but have at least some few double bond systems. And in all other cases where is lipophilic systems with not enough heteroatoms, then you can do distinction indeed by silver, which is pi selective Lewis acid, and nicely can complex different pi systems in different way. And for sure, it's as every chromatographic method is not unique, that no guarantees that you will get always separation. But in this particular case, it really helped really a lot. And what is again for student audience, it perfectly works also for TLC plate. So if you need, actually, you can immerse your TLC plate in silver nitrate, dry it, and you have your TLC plate modified with silver, and you can directly check your reaction, and those isomers, allene or other system, nicely have spots which are divided on TLC plate, just for visual searching of reaction.
Thanks very much. And I can imagine you don't have to throw away your column afterwards. If your
Yeah,
samples are not too dirty, you could
yeah,
follow,
exactly.
right?
So that we for sure the silver is sensitive to light, so we wrap a column in foil, and it's up to 10 to 12 chromatographic purifications. It's quite active still.
Okay, thank you. More questions or comments? Apparently a very clear lecture. Maris, thanks once again. And then we go to the next speaker, who's Professor Edgars Sunna from Latvian Institute of Organic Synthesis, who will present And last year we had him at the Dutch National Chemistry Conference Change in the Netherlands. There he gave a very nice lecture indeed. So I'm looking forward to again to a lecture of Professor Edgar Suna. The floor is yours, and I will now also give over the lead of the webinar to Maris.
Thank you, Adrian. Can you hear me?
I do hear you, and I
Yeah.
see your presentation as well.
Excellent. Thank you for the kind introduction. And today I will present our recent work on the development of stereoselective approaches to chiral sulfonamides and both cyclic and non-cyclic chiral sulfoxamines. So sulfoxamines are widely used nowadays in medicinal chemistry and drug design as bioisosteres of sulfones. And one of the most straightforward approach to sulfoxamines is the formation of sulfur-carbon bond by stereospecific sulfur-selective alkylation of readily available chiral sulfonamides such as L-butyl sulfonamide. Unfortunately, the alkylation usually occurs at the more nucleophilic nitrogen atom or at oxygen, leading to N-substituted sulfonamides or O-alkyl sulfonimidate esters, not shown here. Sulfur-selective alkylation is possible. However, it requires sterical shielding of nitrogen atom as demonstrated in our earlier study. Alternatively, electronic attenuation of nitrogen nucleophilicity also helps to reverse the alkylation selectivity from nitrogen to sulfur center. For example, Maruoka has recently demonstrated sulfur-selective alkylation of N-pivaluryl sulfonamide. Even though this approach is suitable to access chiral sulfoxamines directly from sulfonamides, cleavage of pivaluryl moiety requires relatively harsh conditions and delivers an unsubstituted sulfoxamines. In addition to these examples, we also observed the formation of sulfur alkylation side product during our total synthesis of pseudotabersanin alkaloids. In our synthesis, we required intramolecular SN2 type N-selective alkylation. However, that worked only for Z isomer of tricyclic sulfonamide. In contrast, the corresponding E isomer underwent sulfur-selective alkylation under identical conditions that obviously proceeded through SN2' mechanism. Importantly, the sulfur-selective alkylation was highly stereospecific and afforded diastereomerically pure tetracyclic sulfonamides. We realized that the observed sulfur-selective alkylation may be developed into general and stereospecific approach to cyclic chiral sulfonamides. Indeed, control experiments with structurally simplified chiral sulfonamides confirm exclusive formation of 5-membered sulfoxamides. Nitrogen alkylation and formation of 4-membered azetidines was not observed under our conditions. In sharp contrast, 1-carbon extended homologue underwent clean nitrogen alkylation and afforded 5-membered pyrrolidine under identical conditions, and 6-membered sulfur alkylation product was not observed. Taken together, these control experiments provide an evidence that selectivity of sulfonamide alkylation is likely controlled by the well-known kinetic preference for 5-membered ring formation. Sulfur-selective SN2' alkylation of sulfonamides proceeded in diastereospecific manner with formation of new stereogenic center at synthetically useful vinylic handle. And notably, T-butyl substituent at sulfur could be readily cleaved by weak acids such as silica gel, delivering cyclic sulfonamides. Excellent reactivity was observed for monoalkyl substituted substrates. Aryl-containing precursors were also efficiently converted to the corresponding sulfonamides. However, furyl and thionyl-containing sulfonamides were formed in considerably lower yields. Sulfonamide with quaternary stereocenter and substrates with additional substitution at double bond underwent cyclization in decent yields. And cyclic sulfonamide possessing 4 consecutive stereogenic centers could be obtained in 30% yield. Control experiments were performed to examine influence of stereocenters on alkylation diastereoselectivity. And epimers at sulfur atom afforded cyclic sulfonamide diastereomers with opposite configuration of stereogenic centers at vinylic substituent. Importantly, in both cyclized products, the vinyl and sulfur oxygen bond were syn to each other. The syn arrangement of the vinyl and SO bonds was also confirmed by X-ray analysis for spirocyclic product. Regardless of configuration of stereogenic carbon alpha to nitrogen, we obtain diastereomers with S configuration at vinylic substituent and syn arrangement of the vinyl and SO bonds. And taken together, this data suggests that the new stereocenter has to be controlled solely by initial configuration at sulfur atom. Data from control experiments allowed us to devise a stereochemical model. A nucleophilic C-phase attack of sulfur lone pair on double bond leads to the favored transition state 1, and consequently to cyclic sulfoxamine with the vinyl anti to T-butyl group. Conversely, rephase attack would result in congested transition state 2, featuring pronounced steric clash between T-butyl moiety and the halomethylene unit. Since the chemistry of cyclic sulfonamides is scarcely presented in literature, we decided to examine their reactivity. As anticipated, base-mediated alkylation was nitrogen selective. However, instead of the desired cyclopropanation of double bond under Simon-Smith conditions, completely unexpected sulfur-selective alkylation to sulfoxamine was observed. Sulfur-selective alkylation under Simon-Smith conditions was also observed for N-deprotonated non-cyclic T-butyl sulfonamide. And notably, the alkylation did not occur in the absence of base or without added diethyl zinc. So we started with NMR experiments to gain better understanding of this intriguing transformation. And NMR study with stoichiometric amounts of reagents showed that separately prepared lithium salt of sulfonamide does not interact with diodomethane. However, the lithium salt undergoes reversible formation of stoichiometric zincate complex with diethyl zinc. Unfortunately, exact binding mode of zinc atom in the zincate complex could not be established by NMR because of the known dynamic nature of complexation. Attempted crystallization also was not successful and only delivered crystals of lithium salt. Nevertheless, Upon the addition of diodomethane to zincate complex, rapid reaction occurred, and careful analysis of the reaction mixture showed the formation of stoichiometric amounts of ethyl iodide and minor amounts of propyl zinc iodide, and the major product was dialkyl zinc intermediate. It is known that reaction between diodomethane and diethyl zinc leads to iodine-zinc exchange and formation of ethyl iodide and Furukawa carbenoid. The carbenoid is relatively unstable and it decomposes through intramolecular rearrangement into propyl zinc iodide, which also was observed in our reaction mixture. And the rearrangement involves 1,2 shift of zinc-bound ethyl group to electrophilic carbon attached to the same metal. Once formed in the reaction mixture, the Furukawa carbenoid either decomposes by 1,2-methylate rearrangement to propyl zinc iodide, or it engages in rapid complexation with lithium sulfonamide, similarly to diethyl zinc. And this should give rise to transient zincates. DFT analysis of possible zincate complexes indicated the chelated nitrogen-oxygen bound adduct as the most thermodynamically stable. Nitrogen-bound adduct was determined to be the second most populated species, whereas oxygen and sulfur-bound complexes are far less energetically favored. And based on mechanistic studies, we propose the working mechanism for the sulfur alkylation. The nitrogen-bound adduct between Furukawa carbenoid and deprotonated sulfonamide undergoes 1,2-methylate rearrangement through 4-member transition state to form dialkyl zincate intermediate. Interestingly, the migratory aptitude of sulfur atom in nitrogen-bound zincate apparently exceed that of ethyl substituent. And dialkyl zincate intermediate loses lithium iodide and after protonation forms sulfoxamine as single diastereomer. Dialkyl zinc intermediates can be transmethylated with trimethylsilyl methyl copper into mixed cuprates, and these can be coupled with allyl bromides to afford the corresponding homoallylic derivatives. Next, we evaluated reaction scope with respect to geminal diiodides. And steric crowding around gem diodocarbon suppresses the alkylation as exemplified by decreased 39% yield of neopentylic product. Despite the presence of double bond favorably aligned for intramolecular cyclopropanation, sulfur alkylation product was obtained in 55% yield. And the low basicity and nucleophilicity of organozinc species allows for introduction of a variety of functional groups such as pivalloyl, azide, phosphonate, and even chloride. Alkylation scope with respect to alpha to nitrogen substituent showed that primary alkyl groups are well tolerated. Less nucleophilic and arylated and acylated sulfonamides were obtained with noticeable drop in yield, 40 and 44% respectively. And sulfur alkylation conditions are compatible with the presence of double bond, triple bond, as well as aromatic iodides. The presence of a hydroxyl group was successfully mitigated by higher loading of reagents. With sulfur selective alkylation method in hand, we explored ways to broaden its applicability. we realized that stereoretentive cleavage of T-butyl substituent followed by iterative alkylation with other substituted diiodides would provide an access to enantiomerically pure SS-dialkyl sulfoxamides. T-butyl cleavage on silicate gel was slow for these substrates. However, BF3 etherate affected the reaction within 1 hour. The stereoretentive character of T-butyl cleavage was confirmed by X-ray analysis of methyl sulfonamide. And neopentyl sulfonamide and functional group containing alkyl sulfidamides were obtained in good yields. Surprisingly, reaction of tertiary butyl-free sulfonamide salts with diiodides in the presence of diethyl zinc was slow and afforded moderate yields of sulfoxamines. We hypothesized that rate of Furukawa carbenoid decomposition is comparable with rate of alkylation for these substrates. Significant improvement was achieved using the unsymmetrical diorganozinc reagent butylphenyl zinc, which combined improved stability of intermediate carbenoid with high reactivity of zinc alkyls in iodide zinc exchange reaction. The modified conditions retained excellent functional group compatibility, and interestingly, the iterative alkylation afforded chiral SS-dialkyl sulfoxamines with 2 similar alkyl groups, which thus far have been difficult to access. Finally, alkylation of cyclic sulfonamides was addressed, and from previous work we knew that cyclic sulfonamides are among the least reactive. So we employed butylphenyl zinc for generation of Furukawa type carbenoid. Unfortunately, that did not alleviate the unusual low reactivity of cyclic sulfonamides. However, replacing the phenyl group at zinc with completely non-migratory dimethyl sulfone fragment improved stability of Furukawa type reagent. Under the modified conditions, 5 and 6-membered sulfonamides reacted equally smoothly. Full retention of potentially epimerizable stereocenters in the 6-membered sulfoxamine highlights the mildness of the procedure. And finally, methylation of poorly reactive Davis sulfonamide and an acylated analog afforded the corresponding sulfoxamines with considerably improved yields. In summary, we have developed synthetic approach toward densely substituted enantiopure cyclic sulfonamides with up to 4 consecutive stereogenic centers. And our method was based on a completely diastereoselective SN2' cyclization and T-butyl cleavage sequence. We have also developed a new synthesis of sulfoxamines based on previously unreported alkylation of sulfidamide salts with Furukawa type carbenoids. And this stereospecific transformation involves an anionic 1,2 methylate rearrangement of the corresponding zincate complex and mild T-butyl cleavage, and subsequent iterative alkylation provides a new entry to variously N-substituted SS-dialkyl sulfoxamines that are difficult to access by other methods. And finally, I would like to thank my colleagues in this project. EuChemS was the main driving force for the project. And he was supported by talented master student Matis Boyars and an outstanding undergraduate student Jonathan Smalgalis. Dr. Artis Kinans helped us with DFT calculations, and we are also very thankful to Dr. Pavel Donets for extremely helpful discussions. And last but not least, we thank Latvian Science Council for financial support. And with this, I would like to thank you for your attention.
Thank you, Edgars, for a wonderful lecture. So we have time for questions, which should appear as already announced in the question and answer site. For the moment, I don't see any, but to make conversation. So I have one question on this stereo model. So you nicely demonstrate the existing sulfur stereo center is responsible for the newly formed stereo center. But what about the matched and mismatched case of this existing carbon stereo center alpha to nitrogen in the starting material? So how does that influence that I didn't catch? Is there are there matched and mismatched pairs, or actually is that existing stereo center on carbon actually doesn't matter at all?
If you are asking about cyclization,
yeah,
then we found that in principle, this alpha to nitrogen stereo center does not influence the newly formed stereo center at vinylic position. There is some deviations in terms of reactivity between those diastereomers, but from optical induction, alpha to nitrogen stereo center does not influence diastereo selectivity of reaction. And everything is controlled by chiral sulfur center.
Great. And another I have, so you nicely demonstrate this organo-zinc intermediates, which can be transmethylated to copper and then trapped with electrophilic allylic systems. So what about transition metal catalyzed cross couplings?
Well, we attempted Suzuki, which is pretty obvious, and we also attempted Negishi. And Negishi reaction went rather poorly, so we observed a lot of side products. It wasn't clean reaction, even though one could imagine clean transmetallation of palladium species with our zincate intermediate. Frankly speaking, we decided not to invest into optimization of palladium catalyzed Negishi reaction because our major focus was synthesis of SS dialkyl sulfoxamines. I believe that after careful optimization, one could achieve also a Negishi cross-coupling, Negishi type cross-coupling between zincates and palladium catalyzed Negishi cross-coupling. But this is something that has to be done.
Okay, thank you. Any other questions? The last chance to ask by typing. If not, then we close here. Thank you, Edgars, very much for presentation and scientific discussion. Thank you. And then we proceed to the next speaker. Who is? I have to check my schedule. So the next speaker is Associate Professor Jānis Veliks. Jānis, are you in?
Yes, I'm in. Can you hear me?
Yeah, perfectly. Waiting for your shared screen.
Sure.
So I can announce, so Jānis Veliks is group leader at the Institute of Organic Synthesis in Latvia and also Associate Professor of our faculty of Natural Sciences and Technology at Riga Technical University. And he is going to talk on C1F1 syntons in chemistry. So please, Jānis, stage is yours. So we see full screen, but now we don't hear if you are talking. You lost sound, yeah, but we heard you in the beginning. We were discussing and you were answering. Everything was fine.
Hello.
Yeah, now we
Okay.
hear.
Okay, some problem with sound. So, okay, I share my screen one more time. Mhm. See? Something with connection apparently. Okay. Do you
Yeah.
see presentation and sound is there?
Now it's both together.
Okay, great. So today I will talk about development of reagents for introducing simultaneously one carbon and one fluorine atom in target molecules. So if we look on the FDA approved drug molecules in 2024, then 64% are still small molecules, which is good for us organic synthetic chemists. And among these small molecules, almost 1/3 are fluorinated compounds. So therefore, development synthetic methodologies and reagents for creating organofluorine compounds is of importance in medicinal chemistry. And there are two major strategies for accessing organofluorine compounds. One is direct fluorination. So we create carbon-fluorine bond using a nucleophilic, electrophilic, or radical fluorinating reagents. And the second approach would be the using building blocks that are already fluorinated somewhere else. And if you would ask synthetic chemist working in the lab, which would be the first choice, and I guess you will get answer that the building block approach would be the first choice if you plan the synthesis or organofluorine compounds, because fluorination, as you can imagine, is not the same as chlorination and bromination due to various reasons. And we wanted to develop strategy where we use simplicity of the fluorination, direct fluorination. However, at the same time, use more developed chemistry forming carbon-carbon bonds. And here we end up with the smallest species, which we still can call organofluorine. And these are one fluorine, one carbon syntons, fluoromethyl, fluoromethylene, and fluoromethine. And we love to call them as Lego bricks for fluorine chemistry. And as you can see, that, for example, this compound fluticasone, which is used to treat allergy symptoms, contains actually all of these motifs. We decided to start our research on developing chemistry for fluoromethylene synton transfer. The problem was that in 2019, when we started this journey, it was actually little known about synthetic methods for efficiently introducing fluoromethylene synthon in target molecules. If you talk about the fluorocarbene, which could be the first kind of choice for fluoromethylene incorporation, then the chemistry for fluorocarbene is quite limited. Mostly it's generated from freons, and also it has quite poor reactivity. And also the carbenoid chemistry, fluorocarbenoid chemistry, although it was quite well developed by for example, Charret, Luisi, Pace, and others, it still requires using fluorohalomethanes as a starting materials, all so-called freons. And there was a little known about fluoromethyl and fluorocarbene metal complexes, which could have, and we thought that there is a huge potential for using them in synthesis. As I mentioned, that mostly this fluorocarbene or fluoromethylene chemistry relied on the freons, and there were no solid reagents for transferring fluoromethylene group known before we started working on that. And there was one exception where Jimbo Hu showed in 2020 this fluoromethyl sulfoximine, which they showed can be used for fluorocyclopropionation of Weinrab amides. Yes, and if we think about carbene chemistry, then of course diazo compounds is the first choice. And if we look, and when we looked at the available fluorinated diazo compounds, then actually the simplest member in this family, fluorodiazomethane, was not known, and it's still not known, apparently due to its instability. And we thought, how could we achieve efficient direct fluorocyclopropionation of alkenes? And we thought that maybe sulfonium ylide could be like a surrogate or alternative to the non-existent fluorodiazomethane. And why fluorocyclopropanes are interesting? Because we can see that both fluorine and cyclopropane rings are important in medicinal chemistry. There are even several drug molecules which contain fluorocyclopropane substituents. Yes, and we started our studies with using fluoromethyl sulfonium salt as our first reagent, and we wanted just to check if we can generate ylide from this reagent, because before it was not really known. And as a model reaction, we chose Corey-Tchaikovsky reaction. And indeed, we were able to achieve efficient synthesis of monofluorinated epoxides, which are actually otherwise very difficult to access. And it turned out that it's efficient reagent and also good synthetic methodology for making such compounds. And most importantly, we could prove that the ylide is actually possible. And of course, fluoroepoxides are interesting, but maybe of less potential application. And then we thought that maybe we could develop fluorocyclopropionation using the same Corey-Tchaikovsky reaction. And indeed, when we used vinyl sulfones as Michael acceptors, using this fluoromethyl sulfonium reagent, we were able to achieve fluorocyclopropionation products. There is a preference to form trans fluorocyclopropanes, in the reaction, and it's due to thermodynamically more favorable due to thermodynamically more favorable form. And we were actually also happy to see that our methodology is being used also by industry. We can see some patents coming out where this approach is used for introducing fluorocyclopropane in various potential drug molecules. Further, we tried to optimize these diaryl fluorometal sulfonium reagents. We investigated their reactivity, and so if we have dichloro substituted a reagent, it's much more reactive. However, if we think about affordability, so the cheapest reagents to synthesize is this dimethyl substituted one. And we thought that this is actually also of good stability. And currently in the lab, we are able to make this on a kilo scale. And what about 5-member drinks? It's interesting that if we use this fluoromethyl ylide chemistry for these nitroacrylates, then we obtain these 5-membered oxazolene N oxides instead of cyclopropanes. So far, I was showing you chemistry which deals with the fluoromethyl ylide, and this requires activated double bonds decorated with electron withdrawing groups, and actually we didn't see any evidence of free fluorocarbene involved in this chemistry. And therefore, there was a limitation of application of this fluorometal sulfonium reagent. And as I already mentioned you, that fluorodiazomethane is unfortunately unavailable, and to achieve this fluorocarbene chemistry, we were looking on the ways to get fluorocarbene metal complexes, which could potentially be used for fluorocyclopropanation of unactivated alkenes. And indeed, after screening various catalysts, we found that iron porphyrin based catalyst is actually capable of capturing this fluorocarbene, and in these conditions, we are actually able to do fluorocyclopropanation of various interesting alkenes, also some complicated natural products. And here we don't need electron withdrawing groups to make this reaction happen. To demonstrate this typical carbene chemistry, which is usually done by using diazo compounds, we showed that these reaction conditions using this iron porphyrin catalyst and our sulfonium reagent is capable to achieve so-called Doyle-Kimsey rearrangement, which is the synthesis of these homoallyl sulfides, now decorated with the fluorine. And here we formally show that we introduce this fluoromethylene synthon into the linear chain. Okay, so therefore we think that we have contributed to this chemistry enough to tell that now the fluorocarbene metal complexes can be used for synthesis. Also, this fluoromethyl methyl ylides derived from sulfonium reagents can also be used efficiently in synthesis. What about the other synthons? We are interested also in developing reagents for fluoromethane synthon, so it would require some additional leaving group attached to the fluorocarbene, and so we were looking at fluorohalocarbines. There are known methods for generating fluorohalocarbines in the literature using either freons or some fluorohalo derived substituted acids or silenes. However, most of them require higher temperatures or harsh conditions to achieve fluorohalocarbines. And so eventually we are interested in performing chemistry as shown here. Here is some work from last year by Quiling Song, where we can basically introduce this fluoromethane synthon in target molecule. And so we were aiming for solid bench stable reagents, which could be activated at room temperature to generate fluorohalocarbines. And here again, we looked at sulfonium salts and this mixed fluorohalosulfonium salts. And I should say that that we were also able to develop the synthesis for all these halogens, chlorine, bromine, iodine, and we also developed efficient method which at room temperature is able to generate fluorohalocarbines. And we have demonstrated that we can capture these fluorohalocarbines using different alkenes to achieve fluorohalocyclopropanes. But here, as you can see, we don't need any transition metal catalyst in this reaction. So, and therefore, we wanted to understand what is the difference between this mixed halogen, fluorohalo, sulfonium reagents and this monofluorinated sulfonium reagent, why it shows different reactivity. And we did a control experiment. We took styrene and vinyl sulfone, and this competition experiment where we used this chlorofluorosulfonium salt and tried to generate either ylide or carbene. And indeed, only the styrene gave cyclopropane, and the corresponding fluorochlorocyclopropane derived from vinyl sulfone was not obtained in this reaction, which actually suggests that we are dealing here with a free carbene chemistry. And it's actually supported also by DFT calculations that actually this alpha elimination for the ylide generated from fluorosulfonium salt can easily decompose. It's thermodynamically favorable process to form the free fluorohalocarbene. However, in the case of monofluoro substituted sulfonium salt, now we get cyclopropanation only of these of activated alkene, the vinyl sulfone 10, which suggests that we are dealing here with the ylide chemistry, not the free carbene. And also thermodynamically, it is uphill process to for this ylide to decompose to free carbene. Here, I would like to switch a little bit to the next topic, and we were thinking about developing chemistry which would give us formally cation radical, fluorocation radical, fluorometal cation radical synthon. And we were thinking, how could we use both radical chemistry and also use this nucleophilic substitution type chemistry? And here actually our attention was to these sulfoxides, and we found no examples in the literature of such fluoroiodo sulfoxides. And we thought that it would be really a good candidate for generating both radicals, and then we could theoretically also use some more standard chemistry. Now, in this case, we could use this as a modular building blocks for functionalizing different compounds, and here we paid attention also to this bicyclopentane chemistry, which could be as a bioisoster of the benzene. And basically, when we irradiate this compound once, this fluoroiodo sulfoxide at 400 nanometers violet light, so the homolysis takes place, and we can use the radical chemistry, and we can do this radical addition to this propylene. And then we achieve such type of sulfoxides, which can further be easily converted to the corresponding sulfonium salts, and then we could use it for substitution reactions with various nucleophiles, O nucleophiles, S nucleophiles, iodine, or N nucleophiles. So in this way, we kind of introduce the fluoromethylene synthon between two different components. And here we showed that this chemistry can be applied for synthesis of bioisoster of the known drug molecule. And now I would like to switch to another monofluorinated one-carbon synthon. So the fluoromethyl synthon on fluoromethyl radicals. So when we started working on this topic, actually there was no examples in the literature of fluoromethoxy radical used in a synthesis. So, and therefore we tried to develop new reagents which would which could generate a fluoromethoxy radical. And here our reagent, our sulfonium reagent, was useful, so we could synthesize a series of different fluoromethoxy containing reagents which derived from N oxides or from this HOPT. And we measured also redox potentials and did studies for testing various of these newly designed reagents for their capability to generate fluoromethoxy radical. And indeed, it turns out that this HOPT derived reagent was efficient for generating fluoromethoxy radical using ruthenium photocatalyst and blue light. And also we worked on generation of fluoromethyl radical, and here we actually developed this fluoroacetoxy iodobenzene, which was also not used in a synthesis before, and using copper photocatalyst and blue light, we were able to achieve oxyfluoromethylation of various alkenes. But in last year, in 2024, Naguib published a very interesting and very useful review about radical polarity, and something that attracted our attention was that if we look at the fluorinated radicals and their philicity, we can see that the fluoromethyl radical has the lowest electrophilicity index and actually quite high, very high nucleophilicity index. And it's actually more nucleophilic radical than methyl radical. And if we think about halogen atom transfer reactions, then we need a nucleophilic radical, which is needed for halogen atom transfer. So because the nucleophilic radicals are capable of stabilizing transition states. For hydrogen atom transfer, you need electrophilic radicals. However, for halogen atom transfer, you need nucleophilic radicals. And usually like stannane derived silicon, germanium, and so on, radicals are used for this type of reaction. And we thought that maybe this fluoromethyl radical could be also used to initiate halogen atom transfer reaction. And indeed, we discovered that this fluoromethyl radical is really efficient reagent for halogen atom transfer. The good thing is that in this type of reaction, we do not see the direct addition of the fluoromethyl radical to the double bond, making this reaction quite clean in comparison to other fluorinated radicals. So, and here the radical polarity plays the role, because the fluoromethyl radical is has low electrophilicity, so it's not adding well to the electron rich double bonds. However, it's good for halogen atom transfer. So here we achieve selectivity. Yeah, we developed a substrate scope for this reaction. And also we can use various complicated substrates for this type of transformation. So, and if we talk about the mechanisms, and here we should say that at 400 nanometers we can directly induce the homolysis of this fluoroacetoxy iodobenzene, and then we generate fluoromethyl radical, which acts as halogen atom transfer reagent. Then we have radical addition to the double bond, and then this second halogen atom transfer process takes place. So we get back iodine into the product. So there is also alternative cycle that this newly generated radical acts as halogen atom transfer reagent. So I hope I have convinced you that these monofluorinated one-carbon syntons are interesting building blocks in organofluorine chemistry, and we try to contribute to this field by developing a range of different reagents and catalysts for achieving this type of chemistry. And also we always try to demonstrate that our reagents and methodologies are suitable for some drug synthesis of drug analogs, and we always show this. And I should say thank you to my group members who have contributed to this chemistry, and funding agencies. Thank you for your attention.
Thank you, Jānis, for your presentation. So now we have time for questions, and there is one already in that question box. So diazomethane is known for being a good reagent to make methyl esters from carboxylic acids. And while it might not have any practical applications, have you tried this for your reagents as well?
No, not really. So because so we actually don't we are not able to obtain this fluorodiazomethane. Actually, this the mechanism how you make the ester from diazomethane, it doesn't involve the carbene. So
It's different, yeah.
It's a different mechanism, yeah.
Because that one forms kind of almost like carbenium ion in between, and then it reacts. Yeah,
Yes.
so.
Mm-hmm.
Okay, any other questions? I guess I can still repeat what we already recently were talking on this chemistry. As you remember, that mechanistic control experiments and calculations, that is it ylide or is it carbene there? So how it was about those other experimental methods, except that you look at the products. So some advanced UV experiments or something else which works very fast to get some experimental evidence of this real carbene being. Because for ylide it's kind of nice and easy because it's a stable species, kind of. But carbene is very, very fast one, but it would be, I guess, a great theoretical importance to experimentally prove it with some kind of physical-chemical method.
Yes, indeed. So we don't have such experiments yet, but I think it's our in our plan to further investigate fluorocarbene chemistry, and we could use these ultra fast methods for doing that. Now we have only this evidence which are based on these reaction products that we can achieve. We cannot exclude that, for example, this monofluorinated ylide actually decomposes to carbene, because 19 kilocalories per mole is still kind of something that is achievable at room temperature, and it could be and what that the carbene is also involved in this chemistry. However, yeah, and at least for us, the potential explanation. So if we think about the free carbene, that then why it's not really reacting with the styrene? So we would expect at least the traces of the fluorocyclopropane formation, but we don't see any. However, we cannot exclude that it's maybe not electrophilic enough, because there's some parallels with what I showed you about this fluoromethyl radical, that actually you can have a electrophilic and nucleophilic carbenes. So and apparently these lone pairs on the fluorine can kind of donate some of this electron density to this fluorocarbene, making it poorly reactive. So the free fluorocarbene chemistry is not really practical. Usually you get really poor yields, and it's really difficult to get any meaningful reactivity. So it's an open question.
Okay. Yeah. Okay, thank you. If no other questions, don't see in that question box. Okay, thank you, Jānis. And now we proceed according to our schedule to Associate Professor Gins Schmitz. Yeah, I see Gins already.
Oh, hello. Do you see my screen?
Yes, not yet in full mode, but it's coming, I hope.
It's coming. Yeah, just a second. Yeah.
Okay, and while it's coming, so it's my pleasure to introduce Professor Gins Schmitz, who is in the sense similar like Jānis. It's group leader, head of the laboratory in the Latvian Institute of Organic Synthesis, and also performs teaching duties at the Riga Technical University as associate professor. And today Gins is going to talk about new adventures in hydrosilylation. So please, the stage is yours.
So yeah, thank you for your introduction. I must say I feel very honored to speak in this mini symposia. And today I would like to share our recent results on the hydrosilylation, mainly focusing on ester hydrosilylation. And what was our motivation by doing this? So it was an old and long-standing challenge in organic chemistry, the reduction of esters towards the aldehyde. So perhaps we all know that it's doable, but it often lacks the selectivity, and it you need to deal with just a second, make a pointer. And so you need to deal with lithium hydride, sorry, with aluminum hydride, which are pyrophoric and generate a lot of inorganic waste. And also, one could wish a higher functional group tolerance of this transformation. There have been some advances in the aluminum hydrides, but seems that they are not kind of used routinely. Just some a few examples in the literature on the synthesis. An alternative to that, so within the past decades, has been the hydrosilylation of esters, which involves these silyl acetal intermediates after the first hydrosilylation step, which can then be cleaved either by acid or fluoride towards the corresponding aldehydes. And it is believed that this method has better chemoselectivity, and it's milder, and it also generates less waste compared to aluminum hydrides. And there has been some examples also on upscale of this transformation. So in contrast to diol, for example, this is also scalable. So it is typically catalyzed by transition metal complexes like iron, cobalt, iridium, and so on and so forth. But one very interesting example is actually this triaryl borane catalyst, which is also called BCF, which also does the job. And in this case, this hydrosilylation is also methyl free. If we think about the mechanism, it's actually very interesting and maybe a bit contra-intuitive to what we would think. So it actually starts here with the complexation of the silane with BCF, forming a complex, and only then the ester comes into the game, forming this what is believed to be the frustrated Lewis pair. And then the silyl group is transferred to the carbonyl of the ester, and finally the borohydride does the job and reduces this oxocarbenium ion. So this was proposed and also experimentally showed well by Warren Pierce, and this SN2 intermediate was proved by Martin Österreich some 20 years ago already. There have been some advancements in the field. So this initial pioneering studies by Pierce, so he showed that esters can be reduced in a I would say decent yield, but maybe not entirely perfect. But that was also not the main purpose of his studies. One thing I would like to point out, which came out afterwards, was the studies the studies by Gagné, where he actually showed that the combination of the borane catalyst and silane is essential to achieve chemos and regioselectivity, and he nicely showed this on working on rather complex molecules. That, for example, BCF in combination with diethyl methyl silane mainly gives the reduction of this electron poor double bond, while, for example, fluoro analog of BCF catalyst in the combination with the same silane gives the hydrosilylation product, meanwhile eliminating also this hemiacetal moiety here. And then I guess the most impressive example and advancement in the field was done rather recently by Tibor Schoos, and he showed that by fine-tuning the electronic and also steric properties of these BCF catalysts, the hydrosilylation yields can be considerably improved and are nearly quantitative. And this hydrosilylation can be done also on a rather complex substrate with different functionalities. And here are just a few examples of this of his scope. And so these catalysts are nowadays commercialized by a Hungarian company, AldexChem, and this is where we came into the game. So because we are collaborating with AldexChem in further development of these hydrosilylation technologies, so these and also similar ones. And we were able to work with Schoos catalysts, and it indeed works very nicely. You can hydrosilylate various esters for aliphatic, aromatic, with also this some heterocycles. This will show later, and it also works pretty nicely with unsaturated systems, so it tolerates triple bonds, double bonds, and as I said, also heterocycles. But here, in some cases, the yields are a bit lower because we also observe the degradation both of the starting material and also in the product in this heterocyclic portion. But nevertheless, it works very well also with the long chain esters, as we can see here, and several rather important functional groups are well tolerated. For example, these thioethers, ethers, even alkyl halides, which are not well compatible with aluminum hydrides very often. And to our delight, we also found that this method works pretty well with appropriately protected glycine esters, furnishing these kind of interesting organic syntones with amino group and hidden aldehyde inside. And of course, it works also with esters and diesters and lactones. So we showcase this methodology also in the toll synthesis of citrus leaf minor pheromone, and by combining the Wittig affination with the hydrosilylation in an iterative fashion, we were able to construct this pheromone in a decent overall yield and in only 4 steps, which is the shortest synthesis of this pheromone known today. And we also found that these silylacetals are actually competent partners in reductive aminations, and they serve sort of aldehyde surrogates, and we showed this on in the synthesis of haloperidol. But if you think about this hydrosilylation technology towards the aldehyde, so we are going via this silylacetal, and anyways, it's sometimes even too stable, and you really need to have an extra step, or it can be done also in one pot, that you need to hydrolyze it either by acid or by fluoride. And then what we were thinking, could we somehow engineer this system in a way that this silylacetal would be water sensitive, and that it could be cleaved just by simple aqueous workup. And we came up with a rather simple solution. We replaced triethylsilane with dimethylchlorosilane, and in that case we actually generate a silylacetal with the silicon chlorine bond, which is still proteolytically labile. And indeed, when we quench this reaction mixture with THF water, so we can isolate in a very good yield the corresponding aldehyde. But what we are thinking, what if we go a step forward and quench this reaction mixture with alcohol or thiol? And in theory, we could directly get to the corresponding acetals or thioacetals. And indeed, to our delight, this really works. And it works even better than this aqueous quench. And we isolated in the first batches already the acetals with 91% yield. And of course, what we did next, we studied the scope of this reaction, and it seems to be rather general. So this method tolerates double bonds, triple bonds. We can also do this reaction on aliphatic halides, aromatic halides, and even some rather appropriately protected amino groups. I must, however, say that we are generating stoichiometric amount of anhydrous H cell, and this method often is not compatible with heterocycles. For example, the pyrene was completely degraded under these reaction conditions. But nevertheless, we were also able to obtain a series of cyclic acetals and also thioacetals. And what was rather surprising that to us initially, it turned out that many of these acetals are actually naturally occurring fragrances, and it's not maybe that often in chemistry that working on some project you can feel some herbal or floral or fruity notes in your laboratories, but this was the case. So yeah, there was some rose notes or others, and so even melon. But what I must admit, so there was also this thioether, which was it was a horribly smelling liquid, so not hard to imagine why. Okay, but moving on, so we were working a lot with these fine-tuned borane catalysts, and in parallel we examined also BCF as a control. And what we were thinking, what is actually the problem in this reduction of esters with silanes catalyzed by BCF? So one thing which is known that, okay, the main impurity is the overreduced product, the silyl ether, but actually the total yield is actually not complete, and something else is going on there. And so one of the first things we tried, we actually properly analyzed all the reaction products from this mixture. And what we found, and what was not known in the literature, that actually we do form also a vinyl silyl ether in this reaction. And this is actually a very interesting reaction, which, as I said, yeah, it's not reported in literature. We thought it would be interesting to develop it further. And to summarize many months of and many failed experiments in one slide, so we were actually pleased to find that by extending this R1 substituent on the ester, we can actually isolate this vinyl ether in rather good yields, actually. Yeah, but here I need to point out that this works mainly with linear esters, not with branched esters, because with those the yields are really low. And also rather good yield was obtained with a benzyl ester. And so we moved on. So but this is what we are doing now. So we are working on the scope of this reaction, and it seems that in general the butyl esters, for example, gives higher yields of the desired vinyl ethers compared to benzyl, but there are some differences between substrates. So it works on aliphatic substrates, which I would say not ideal, but very decent yields. You can do it also starting from the lactones. So this method also tolerates one, but just one alpha. Well, obviously one alpha substituent on this ester group here. So this method works pretty well also with aromatic esters, also with aromatic esters with bromine substituent or bipene substituent. But funny enough, it doesn't work with phenyl acetic acid esters. But this we're still studying. Why is it so? It also works with unsaturated with double bonds, with triple bonds. It also works with in thioether series. Also, alkyl halides are tolerated by this method, and even heterocycles. What is really interesting is that there are a series of substrates which actually stop at the silyl acetal stage, and we'll get to that a bit later. And although it seems to be a rather simple reaction, we were very interested in the mechanism. So how exactly is this happening? And so this is our catalytic cycle, which we believe takes place in this reaction. So we are not doubting that the first step is this Pierce-Osterreich mechanism, which I showed you earlier. So we start here with ester. Okay, we start actually with the BCF. We form a complex between BCF and silane, and then via this FLP intermediate, this corresponding silyl acetal is produced. So, but the next catalytic cycle, which we believe is taking place, is actually a bit different. It's not the Pierce-Osterreich type mechanism, but we believe that the second cycle is actually the Lewis acid. Well, I would say more classical Lewis acid activation. Thus, the BCF complexes to the less substituted acetal oxygen, and then this bond is dissociated into lone ion pair, which then ultimately eliminates butanol in this case and furnishes the corresponding enol ether. And so what is important to point out that this transformation from silyl acetal towards the enol ether doesn't happen just with the borane catalyst. We really need an extra silane to make this work, and what we believe is happening here. So this third catalytic cycle is actually is the driving force for this whole sequence from silyl acetal towards the enol ether, and this is maybe not experimentally so well studied at least we couldn't find in the literature, but what is believed is happening. So we are again forming a similar borane silane adduct like in Pierce mechanism, which is then transferring the silyl group to the alcohol, and then afterwards hydrogen evolves, and that is it. So we also studied this mechanism more in detail experimentally, and first I must say, first this was suggested actually by DFT, because these are, if you look at the transition state energies, these were the most favored transition states from the DFT point of view. But of course, we wanted to have some experimental proof for that, and we did a lot of labeling, and some results are shown here. If we label the silyl group in the silyl acetal, it ends up in the product. So this is what we thought, but this is just to confirm that it's really like that. So the next thing, we also did some kinetic isotope effect studies, and what we see here, that rather obvious, the alpha deuterium from the silyl acetal ends up here in this hydrogen gas, or let's say call it HD in this case. And we had also a hypothesis that perhaps this elimination proceeds via some kind of E2 process, but actually, at least judging by the kinetic isotope effect, we believe is actually E1 type, because for E2, usually the kinetic isotope effect is much larger. But the most interesting, and I think this also is one of the strongest kind of arguments for our proposed mechanism, we found when we studied the kinetics of this reaction. So what do we see here in this plot? So we, at the very beginning of the reaction, so we see that the concentration of the ester decreases and the concentration of the intermediate silylacetal increases. That totally makes sense. But what was really interesting to find was that when we look at the concentration of this final product of the silyl vinyl ether, so it starts forming only after all ester has been consumed. And what we believe what is happening here, so first we have this piezosteride catalytic cycle when the ester is reduced via this FLP intermediate. And while we are still having the ester in the system, we are operating via this FLP mode, and the second Lewis acid activation step doesn't take place, and it starts only after all the ester is consumed, and we can't have this FLP intermediate anymore. And this, we believe, it also explains, for example, why these while the esters containing polar fragments in the molecule, like this indole azide, also this phthalate derivative or amine, why these substrates stop exactly at silylacetal stage? Because in these cases, we believe that we are actually stuck with this FLP scenario, and we cannot get enough of the free Lewis acid to do the elimination step. And so to wrap up, so I hope I was able to convince you that that very small changes in the ester or the silane or the catalyst structures actually help us to deliver different reaction products in very good yield and selectivities. So, and yeah, acknowledgement. So I'm very grateful to my group and Rebecca in particular, who did most of these experiments, and also our FLPP project for the financial support of this work. And I would also like to thank these two gentlemen, Gabor and Joseph from EuChemS, with whom we are having a very fruitful collaboration in development of several silylation technologies. And as many speakers of this symposium mentioned before, so big thanks goes to Associated Professor Artis Kinants for the DFT calculations, and Jordi Bourret, who is helping us with the kinetic studies of our reactions. So thank you all for your attention, and I will be happy to take questions.
Thank you. So the floor is open now for discussion. So in the question box, there is none for the moment, so I can ask just in person. So regarding that your last piece of work, which was on silyl ether synthesis, so I saw, okay, you mentioned that longer chains or some specific alcohols as an easier to eliminate. What about trifluoroethyl group? I haven't seen that one, which would be better leaving group to create in more maybe productive ways at oxycarbenium ion. Have you tried that one?
You mentioned trifluoroethyl, right?
Yeah.
Yeah. This we tried actually. We have also had a lot of hope on that, but that doesn't work.
Because it was not on the slide, so it was
Yeah,
hidden.
it was not. I actually, as I said, this was just a summary of many months of
But
stuff.
then can you still elaborate on that? Because anyhow you have to that this alcohol or this alkoxy group should go
Yeah.
to form this either depends how you call it, either oxycarbenium ion or activated aldehyde or whatever. So if electron withdrawing properties don't help, so what exactly then helps this leaving group to leave? So what is the that productive equilibrium then?
So what actually, what we think and what we observed also in the control experiments, that it somehow helps to move the catalyst away from this side of this reaction. I mean the reaction side, because what was rather evident, we did also a lot of studies with methyl ester, for example, and in that case, when I think I mentioned here that we did the labeling studies. And actually, when we do the labeling studies with the methyl ester, we do see that there is scrambling between the products. So there are actually many, or okay, maybe not many, but at least two mechanisms operational which go parallel. So I would say it's maybe the sterics, but also not too much of the sterics, because if you put alpha branched, if you make alpha branched esters, they also doesn't work. And I believe these are too crowded. There's obviously a sweet spot in those alkyl groups which react and which don't, because it's sometimes easy to shut down the reactivity
And
completely.
in that context, did you try beta substituent, something like closer to neopentylic or stuff
No,
like that?
this we didn't. We were so this all was based also in part on the esters which are more accessible. So we thought, okay, it would be nice to have ethyl esters because many of those you can also buy. These unfortunately didn't work so well, so we stayed at something simple like butyl ester and butyl ester or so, to have it convenient as possible for yeah,
Okay.
as a method in general. But these we haven't tried, I believe.
And another question I would have, it's as you nicely mentioned, that you can transform your intermediate products into stable acetals, but still those are symmetrical acetals. So is there a possibility, as you have two different substituents, alkyl and silyl, substituent is still an acetal, but variated. So is there possibility that you selectively make non-symmetric acetals, taking account that actually you have that already difference in your intermediate product?
Well, this will leave for maybe the next lecture, because yeah, there is actually a possibility to discriminate between these two substituents in the acetal, but this is we are pretty early on this research, so this I was not presenting, and well, yeah, I will keep you up to date in the following talks and papers. But in general, yeah, there is such an opportunity. Maybe I think there's still much to be discovered in this area of unsymmetric acetals, but I think it's a bit early to tell about that.
Okay. Thank you very much. So in the meantime, no additional questions in the question box. So we stop here. Thank you, Gins.
So thank you for your kind attention. Yeah.
And now we proceed to University of Latvia. And Edvards Baķis is ready. So Edvards is a young researcher. Also, he's a group leader. And now he's going to talk about ionic liquids as media for organic transformation. So please, Edward, the floor is yours.
Thank you, Maris. Thank you for organizers putting together this meeting. I apologize if I will switch on the camera. This whole thing will unfortunately crash. I tried it several times, so have a look at my picture now, and let's stick to the most important, to the topic. So ionic liquids are very much different from what we have heard today, and there was an period where a lot of work on synthesis was done, like using them for media, and there are several reasons for that. But before we go for that reasons, first of all, how we define what an ionic liquid is. This generally is any ionic type compound that can form a fluid stable enough to provide liquid at room temperature. And one of the fathers of ionic liquids, first discoverer, as we heard today, his name already, is Paul Walden, born in Latvia. And his most famous discovery is the ethyl ammonium nitrate, which he was not aware of significance of at the time. However, these days, the ionic liquids have moved towards more stable compounds, and one of the most common ones, most archetypal, are imidazolium ionic liquids with the hydrophobic bis imide anions. So, as a liquid, it's rather viscous. It's 51 millipascal. Water is around 1, glycerol around 1000, melts under 2 degrees Celsius. But why it keeps to be fluid? So one possibility is that the cation lacks symmetry. There is a possibility for rotational freedom. Charge is rather delocalized. And similarly for anion, charge is rather delocalized. There are several conformers possible, and the conformers are very flexible. So how to guess in advance if the ionic liquid is going to be a good one or a bad one, let's say a liquid one or viscous one, all lays into the said factors, but mostly the properties are dictated by the properties of the anion. And here you can see a very nice explanation on how ion design can really fine-tune the liquid range and melting properties and viscosity. And if we look here on the graph, on x-axis we have CSNS dihedral angle, and on the y-axis the SNSC dihedral angle. So if we vary these dihedrals, we can see very easily if we have nitrogen in the center, there is a very flat energy surface for these different conformers, all very similar, and in fact the cis and trans differ by very little, 3 to 4 kilojoules per mole, which is accessible at room temperature. If we switch to only one modification in this ion, so switch to carbon atom, we end up with much bigger formational energy barriers. As a result, you can see that these two ionic liquids differ very much in their properties. One of them is rather fluid and low melting, the other one increased viscosity and melting point. So why do we care for ionic liquid at all? So the era when we believed ionic liquid will replace ionic solvents in laboratory have passed. So now the field is focusing more on the large-scale applications. That is imperative for industry. And the advantages are because there are very many of those compounds possible, around 1 million or more, and they are non-volatile. They are capable of specific interactions and conduct electricity. So this is in stark contrast to some limitations that we have for the molecular solvents. And here you can see some rather large-scale industrial processes that have been implemented since 1996. And just to give you brief examples, one of them currently still in use is the BASF Basel process, where the phosphorus compound is turned into its ester. And what its drawback so far has been is that the byproduct, the acid scavenged salt, is very high melting, so forms solid in the reaction mixture, different separate. While if we use methyl imidazole as a base, we can use a byproduct that itself is liquid, and in fact can afford two separate phases when the top phase is pure phosphine product, the lower phase is the protic byproduct, which can be recycled. And by implementing a special reactor design, we can increase the reactivity by 10,000 times the productivity of this process. Another very recent area which already has been commercialized and is in action in Canada is production of alkylate from lightweight hydrocarbons, which usually are byproducts in petrol cracking. So far, the golden standard has been use of neat hydrofluoric acid or neat sulfuric acid with very appreciable amounts of these compounds in the reactor. And so far, there have been accidents, of course. One of them is in Marathon City, 1987. And till this day, I read there are around 50 deaths involved with the handling of this compound alone. So another very acidic media can be used, and this is chloroaluminate ionic liquids, which significantly improve the process by reducing the necessary volume in the reactor, and the catalyst can be regenerated on site. So there are around 300 plants globally using this process, chemical manufacture process, so there is a demand for replacement. However, if we want to do a more sophisticated catalysis, we would like to make it scalable. And for ionic liquids, the only way how to do it is the so-called supported ionic liquid phase catalysis, SILP catalysis, which in fact is impregnating a solid support with ionic liquid, in which, if necessary, catalyst can be dissolved and the reactant stream pass through to convert this into a product. So very scalable, industry well-known procedure. However, we require to know the mechanisms how reactions take place in ionic liquids on first hand to be able to design such processes. Ionic liquids are very polar in the sense that our intuition says, but in fact, if we measure the dielectric constants, they are quite narrow range, 9 to 15, the dielectric constant, while for the molecular solvents we know today it spans very much. So other means of characterizing polarity are needed, and very useful measure for that have become solvatochromic polarity measurements. So they are based on the UV-vis spectroscopic response of these probe molecules, and absorption maxima of which are then transformed into arbitrary polarity parameters. So when we started to study the so-called Knoevenagel condensation, a very widely used and old reaction, we wanted to bring some clarity on top of the thousands and thousands of papers who just mixed the two carbonyl and CH compound in ionic liquid and said, oh, this performs greatly. So we wanted to understand why. And we selected a range of ionic liquids that differ by the cation structure and anion structure, and these are the polarity parameters. You may see they are strongly dictated by anion nature. You see the beta value, hydrogen bond accepting capability is higher for more basic anions, and for those cations which can form some hydrogen bonds, like the C2 position in imidazolium rings, you can see consequently higher acidity alpha values. What we did, we tried to use these quantities to understand why the Knoevenagel condensation proceeds so well in ionic liquids. So this is an example we selected because the kinetics were easy to control. However, on all other instances, it's basically instantaneous. You mix the two compounds, the 5 minutes, the product is formed. And what we did, we measured the reaction rate constant, and we noticed that there is an increase in rate constant if we start to move from bromine to chloride to dimethyl phosphate anions. And how to explain that? We did some NMR studies to understand what affects the hydrogen bonding acceptability and how the that in fact impacts the solute-solvent interactions. And we noticed that the beta parameter correlates linearly with the CH shift in the carbonyl compound, the active methylene compound. And this is explained by the fact that it is mainly the anion which can interact with the substrate and therefore affect the chemical shift change. If we try to see if the carbonyl group perhaps can be activated in the ionic liquid as well by means of cation hydrogen bonds, we do see that this trend is less clear. And that is not the main reason, perhaps, why the reactivity is so good in basic and ionic liquids. How to rationalize that? We use the so-called linear solvation energy relationship, where the quantity on here is a property of reaction you want to correlate with property of the solvent, and the coefficients A, B, and S would be the coefficients that describe the significance of the parameter of the solvent that has impact on reactivity. And after studying 6 different possibilities, the statistics suggests that the most statistically significant correlation is when the LSER equation involves beta parameter alone. So then we have the very low p-value, which suggests that it's primarily the high beta values of these solvents that have a positive impact on reactivity, while all the others, according to the low p-values, would not be a good guess to explain this activity. So that is what people have noticed already, picked up from our work, and cited it in other associated studies. So another type of reactions we recently have investigated in greater detail is the copper-catalyzed Crick reactions. And you all very well are familiar with this mechanism where there are 2 copper atoms in the transition state, where the first one is pi-coordinated, second one is forming a covalent copper acetylide bond. And after some rearrangements, you eliminate back the copper and reaction starts again. So some significant steps are a loss of acetylenic proton and reprotonation. So we suspected there might be something to do with the acidity or how the ionic liquid handles acids in the media. We selected a modal reaction where we loaded 7 mol% of copper catalyst in different ionic liquids. We selected those which are of functionalized side chains, which have aromatic or aliphatic cation core, and a range of anions which differ with their basicity, supposedly also with their hydrogen bond accepting property. We investigated 4 different copper catalysts. The first one known to all of us is the conventional copper 1 iodide, and then some other catalysts which in all instances were aimed to be soluble in the media investigated. And so when we selected the most conventional ionic liquid, investigated the 4 catalysts, what we noticed in the kinetic curves is that they differ very much based on what catalyst you use. So if you use the copper iodide complex and acetonitrile complex, you see there is some induction period before the reaction even starts. While if you use the bromide complex, the reaction rate is rapid and almost instantaneous. What about copper iodide? The copper iodide, unfortunately, was not soluble in the medium, such so was not investigated here further. We went and compared these catalysts in a different ionic liquid that very much differs from the first one, as it is hydrophilic. It's also very coordinating, and we noticed a remarkably longer time for a reaction to reach completion. And additionally, no induction periods could be observed anymore if we switch to this coordinating dicyanamide ionic liquid. Interestingly enough, copper iodide could be very easily solubilized in this, which is not very trivial in all other instances where the catalyst is used. To explain that, further went on and looked into detail what happens if the water content of the ionic liquid is changed. So using dry ionic liquid, indeed, in all instances, we noticed this induction period in the non-coordinating ionic liquid, while the effect of water was not as pronounced in case if we use the coordinating ionic liquid. And if the water is added, in fact, these induction periods disappear completely, suggesting that there might be several explanations for this. Either this is increased transfer, which appears in the reaction mechanism, or probably a competing ligand that yields to more unsaturated, easier catalyst dissociation, or perhaps it's water that hydrate the iodide counteranion and therefore facilitate coordinatedly unsaturated copper formation. Maybe the carbines could be blamed for this. We heard about carbines today, and in fact it's known that transition metals facilitate formation of carbines from imidazolium salts very easily. And to rule this out, we switched for a aliphatic cation core, where in presence of this catalyst, no drastic change in the kinetic profile was seen. So thereafter, we investigated what happens if the ratio of the reagents is changed, and the stoichiometric reaction is displayed in red in this system. If we use excess of benzyl azide, we don't see much difference. However, using excess of phenylacetylene makes the reaction, instead of faster, what you might expect, but much slower, which we explain with the fact that it is in fact the two copper ions that are necessary for the reaction mechanism. If we move back to the reaction mechanism here, you may easily see that two copper ions are needed. So if we increase the concentration of the acetylene and the reaction goes down, that obviously suggests we are limiting the amount of available copper for the second step. And therefore we can draw some interesting conclusions from the study that before that, copper dissociation from the complex is the first thing that has an impact, as that eliminates or forms the inhibition, the initiation period, and secondly, it is the availability of the extra copper ion in the solution, which limits the rate in some ionic liquid. This same was reconfirmed if we analyze some functionalized ionic liquids. As soon as we introduce those ether groups in the side chain, you already see induction period appearing. The reaction rate is slower, which perhaps is associated with the copper coordination to these ether chains. If we switch to some silicon functionalized ionic liquids, which you would not expect to have a drastic change, then still the initiation period persists, while surprisingly, if we use a siloxane linkage in the side chain, even then the very otherwise coordinatively unavailable oxygen in this siloxane bond, even then it trends to coordinate the copper ion and therefore reduce the reaction rate. And finally, you saw there was a base participating in the reaction mechanism, and obviously this has to be explored as well. And when we use a little additive of the basic ionic liquid, which has a tertiary amine in there, the initiation period disappears. If we switch to a pure ionic liquid with a basic functional group, the reaction rate goes up very much so. The effect, again, is less pronounced in pure dicyanamide liquid, where you see that if you add the base functionalized ionic liquid, the rate goes up, but still the reaction is slow, which we still can explain with the fact that an ion of the ionic liquid is predominantly the one that is responsible for coordinating or holding the copper ions of the catalytic cycle. So what is the best to do in that case is to go for a neat ionic liquid with the basic functionality. the copper complex with the most labile structure. So according to the soft acid-base theory, bromine copper dissociation would be most expected. And in such scenario, we be very quick, as quick as we wish. We can't run to the NMR spectrometer. The reaction is complete at room temperature in just under 5 minutes. Now, in summary, we can say that in coordinating ionic liquid, copper complexes dissociate rapidly, but thereafter copper ions remain strongly associated with ionic liquid 9. Different story happens in weakly coordinating ionic liquids, where copper complex dissociation is rate limiting. Water or another ligand facilitates this dissociation, and according to the stoichiometric ratio study, we see the first copper ion in the mechanism is bound strongly and rapidly to acetylene, while the second binds much more difficultly, and therefore the excess catalyst acts as poison for the catalyst. Addition of base in all instances increases the copper acetylene formation rate, and therefore also the reaction rate. Short, I would like to thank you for listening today. This is University of Latvia campus. The next building is soon to appear, hopefully. Now there are 2. Feel free to visit our group website. I thank my colleagues and students, and as well as funding agencies for supporting our work. Thank you very much.
Thank you, Edwards, for this journey into world of ionic liquids. So we have time for questions, if there are any in the question box, not that I would see. I would have just like educational question about this, your newly introduced siloxane sidechain in ionic liquids. So how are the stability? Because if you operate with structures, with the products which also have some nucleophiles in it, like halides, etc., aren't there some pretty fast to cleave?
You mean the siloxane bond itself?
Yeah, that sidechain, yeah.
Yeah, the siloxane bond itself is one of the strongest ones known, in fact. But if you choose harsh enough conditions, it's possible to observe that at some point the silicon carbon nitrogen linkage is the one that would first fall apart. It has rarely been the case in our experience, in fact.
Because if you have, as soon as you have one electronegative atom on silicon, so it becomes more susceptible for some nucleophile addition, and then the system is activated. It's a silicate complex which can do some other stuff.
Yeah, I agree with you, and so far, in fact, several people have asked about this, but there have been very few instances when we actually can observe this easily. So I believe there is a rather large spherical crown around this active center here, and the rotational barrier for siloxane bond is very low. So in fact, this sidechain acts as a large propeller and somehow screens perhaps the attack site.
Okay. Any other question? If not the case, then yeah, thank you, Edwards.
Thank you very much. Sorry for the camera. Good luck.
Yeah, thank you. And now we proceed to the last speaker of today's session of highlights of Latvian organic chemistry. And that's our young researcher, Georgijs Stakānovs, who has been busy and still is busy with natural product synthesis and semi-synthesis. Just as we have different views on Latvian chemistry. So far it was methodology and also physical organic chemistry. And now we proceed to synthesis and synthesis. So please, Georgijs, floor is yours.
Hello, can you hear me well?
Yes, we hear you well.
Okay, so let me share screen, and do you see it?
Yeah, we see and hear it.
Yeah, okay, good. Greetings, dear audience. It is my pleasure to participate in this symposium, and my talk will be devoted to valorization of terpene called beta-caryophyllene and its uses in semi-synthesis of exotic terpenoids. Caryophyllene as a substance is known since 19th century, when it was firstly isolated as one of the main constituents of the cloth oil. And of course, people this time had no idea about its structure, how it looked like. In 1892, Otto Wallach prepared first crystalline derivatives of caryophyllene, and around that time, it was clear that the caryophyllene belongs to sesquiterpene family. So it's terpenes with 15 carbons in the structure. However, the precise structure and, of course, the stereochemical configuration remained yet a mystery. In 1930s, in the absence of modern spectroscopic methods, Ruzicka firstly cautiously proposed the structure of caryophyllene as cyclobutane condensed fused with the cyclohexene ring, but still some doubts remain, particularly because of the unusually high reactivity of one of the double bonds. And 2 decades later, Derek Barton, Sir Derek Barton, elucidated the structure of caryophyllene as being a dimethyl cyclobutane condensed with unusual E-cyclononene fragment, and this cyclononene fragment bears also an hexamethylene substituent. And then this unusual structure was finally confirmed by a group of E.J. Corey in the total synthesis of the caryophyllene. So, bottom line, the caryophyllene is the cheapest sesquiterpene available on the market, which is, of course, renewable since it stems from biomass. It possesses 2 stereo-defined chiral centers and 2 double bonds with different reactivity, and as well as underexplored potential in synthesis of rare terpenoids that have either biological activity or some intricate structural features. And the strategy of functionalization employs the difference of reactivity of double bonds. In caryophyllene, the trans double bond is considerably more reactive, allowing for generation of strategic building blocks A and B. In turn, beta caryophyllene oxide, which is also commercially available, the epoxide masks the endocyclic double bond, and the alkyl functionalization goes to exocyclic double bonds, generating building blocks C and D. So it is known that caryophyllene readily generates other sesquiterpenoid scaffolds depending on conditions applied, whether it's carbon-cation cyclization. But note that in this reaction, we primarily generate mixtures of compounds. Radical reaction as well, where you can just synthesize, for example, humulane, microcycle, and oxidative cleavage. So the latter approach was used in our development of concise synthesis of biologically active sesquiterpene lactones, runfolones A to C, from beta caryophyllene, which was dihydroxylated, and then the dimer was cleaved, and pigment oxidation gave rise to the beta-caryophyllonic acid. And this acid was lactonized to the roomphilone A, which was then alpha-beta dihydrogenated to roomphilone B. And simultaneously, this caryophyllonic acid can undergo epoxidation with lactonization to generate roomphilone C. Now, this approach did produce the desired compounds rapidly. However, it generates also the epimers of the roomphilons HC, and that actually prompted us to focus on the bi, tri, and tetracyclic terpenoids to make the structure more rigid, and then therefore enhancing the substrate-controlled stereoselectivity. But still, we were pleased about this result because also we confirmed the configuration of the newly formed lactone cycle. So the first step in our study was the synthesis of the roomphilolide J, natural product, which belongs to the rare class of the disescoterpenoids. So two different sesquiterpene fragments combined in one molecule. Although the biological activity of target ester is not reported, the corresponding alcohol enhances the generation of the superoxide anions by human neutrophils, and rufolic acid A displays also anti-inflammatory activity. So we started the synthesis of two main constituents of the roomphilolide J. So initially, caryophyllene was selectively dihydroxylated, and then in the acidic media, cyclization happens, and we get our alcohol particles, epoxycaryophyllene alcohol. The synthesis of roomphilolic acid was started from the beta-caryophyllene oxide, which was isomerized in strongly basic media to allylic alcohol 11. Then the acid catalyzed pinnacle rearrangement accompanied with transaminal cyclization gave rise to the aldehyde, which was then oxidized under Pinnick condition to give us the roomphilolic acid A. And the challenging part, of course, the formation of the ester bond between two sterically hindered fragments. And conventional methods like the conversion of the acid to the acyl chloride was not successful. The esterification using carbodiamides, HOPT and DMAP also failed to give the desired product as well. But the most successful was the conversion of the roomphilolic acid A to the acyl fluoride using dust reagent, and acyl fluoride smoothly reacts with the alkoxide, lithium alkoxide 14, to generate target products, gram scale, and in good yield. So the next step of our study was synthesis of anti-inflammatory, now terrestrial natural products, linearyophyllines A to C, and out of these three natural compounds, linearyophyllin B displays the most potent inhibitory activity. So we synthesized this linearyophyllin B first. Beta-caryophyllene oxide was dihydroxylated. However, it produced the epoxydiol 15 with undesired configuration of C8 in comparison to the target compounds. Moreover, epoxydiol 15 displayed the ability towards cyclization in weakly acidic media, forming a natural product Rumfeld-like H. But to tackle the problem of the wrong diastereoselectivity on the C8, we then cleaved the diol, generating cobosome, also natural product, and then isomerizing to the cobosome to the isocobosome. And this isocobosome helped us to synthesis in the synthesis of the linearyophyllin B. So this allylic alcohol isocobosome was protected by TBS, and then the nucleophilic hydroxymethylation happens stereoselectively. So initially, the attack of the silyl methyl grignard stereoselectively produced the silyl alcohol, which was submitted to the Tamar oxidation, and we finally have the C8 stereo configuration as our needed stereo configuration. And then the TBS group was cleaved in acidic media to generate linearyophyllin B, whose structure was proved by the X-ray crystallography. Then linearyophyllin B, which possesses an exocyclic double bond, was isomerized to the endocyclic double bond using potassium 3-aminopropyl amides. And then the mixture containing both starting material and the product was silylated to facilitate the chromatographic separation. And then the silyl groups were cleaved, and we generate linearyophyllin A. And this structure was revised at the C5 position. So we didn't have to invert the secondary alcohol. So the spectrum data completely corresponded to the natural isolate. So in the to the synthesis of the linearyophyllin C, it was started with the allylic alcohol 11, which was epoxidized to the epoxy alcohol 25. Then Payne rearrangement happened, and we generate the primary primary alcohol 26. The primary alcohol was then methylated, and the methylate was reduced by the superhydride, generating the epoxide 28. But after dihydroxylation and acetylation, we obtained three products. However, spectra of neither corresponded to the spectra of natural linearylphenylene C, especially in the case of compound 29, which was proposed structure of natural linearylphenylene C. But the divergence were not so large to suggest some connectivity error. Most likely, the correct structure of linearylphenylene C was belongs to the other stereoisomer. So thus, we aimed at synthesis of all possible stereoisomer, hoping that one of them would be the desired. Thus, epoxydiol was acetylated to give rise to the epoxy acetate, whose spectra did not correspond to natural linearylphenylene C. The same thing happened with diastereomer 34, which was synthesized from diol, Williams epoxidation, and then dihydroxylation and acetylation. But finally, the true structure of linearylphenylene C was in the end attributed to the structure 38, which was obtained by using Korey-Chaikovsky methods to generate this dioxide 36, which was cleaved using cesium acetate in crown ether in DMF solution, that produced diol and the xanic acetate. Diol was smoothly converted to the acetate using standard acetylation conditions. Next, we aimed at exploration and resolving the stereochemical ambiguity of euphorine E, possessing this extremely rare bridgehead epoxide moiety. So only this euphorine E and also one other natural product called salsolene oxide possess this moiety. The carbocationic transformations of allylic alcohol 11 are known in the literature. However, the carbocation transformation of enone 39 were not known. And surprisingly, the Lewis acids catalyze the formal 2+2 cycloaddition to propylene containing ketone 40. But the DFT calculation did not show the reason for the diastereoselectivity of this reaction, since the difference between transition states is not too big. However, they displayed that this reaction happens without with intermediacy of the tertiary cations. The propylene ketone 40 was reduced to the alcohol 41, which is a non-terrestrial natural product. The methylation and solvolysis gave rise to bridgehead olefin 43 via secondary generation of the secondary carbocation A, and then the cleavage of the CC bond of the new phosphate butane, and then the hydration. But the epoxidation of alcohol 43 with MCBA gave rise to the bridgehead epoxide isoeuphorine E, as its spectra did not correspond to natural bridgehead epoxide. And the true structure of euphorine E was synthesized by the solvolysis of allylic mesylate 45, which was quite unstable on isolation, and that exclusively gave diastereomeric bridgehead alcohol 46, which was epoxidized to yield the final product, euphromin E. To elucidate the diastereoselectivity of this solvolysis, the DFT calculations were also performed, and in this case, they showed the preference of one diastereomer over another due to the fact that the departure of mesylate preferentially happens when the pi orbital overlap the antibonding CO orbital, resulting in the hyperconjugation, and thus it facilitates the cleavage of the mesylate when it is in the equatorial position. And this assures the complete stereoselectivity, which corresponded to the synthetic results. And the latest steps in our study was decided to design the synthesis of rumfolitines AC, unique chlorinated caryophyllene nor-sesquiterpenoids. Nor means C14, so nor-sesquiterpenoids is one carbon less than sesquiterpenoids, and they possess usual ketal moiety. But no synthesis was reported, only unsuccessful total synthesis, and that stimulated us to design synthesis from caryophyllene oxide. Previously we noted that isopropyl exists as a hemiketal also in the deuterated chloroform, and deprotonation of the isopropyl gives rise to the hemiketal anion, which can be trapped by methyl iodide, and we have the ketal 49. So this ketal 49 was used in the synthesis of rumfolitine A. So dihydroxylation and diol cleavage gives us the ketone, and this ketone reacts with methyl magnesium bromide to produce tertiary alcohol 59 in a stereoselective fashion. Then chlorination produced by the action of the thionyl chloride, but also it produced quite unseparable elimination product 48. So we used osmolysis to separate two of them, and that facilitated the separation. So the chloride was demethylated using TFA, and then we synthesized rumfolitine A with a revised structure. So in the proposed structure, the bridge of the oxygen bridge was in the looking behind, and then it's looking at the front in the revised structure. Now on the synthesis of rumfolitines B and C, we started from the epoxy diol. We protect the diol moiety with carbonate, and then it is the epoxide was isomerized to endocyclic halidic alcohol, and then the cleavage of the carbonate and cleavage of the diol gives rise to the keto alcohol 62. And then the synthesis of two diastereomers happened by the action of the MCBBA, one of which happened to be rumfolite C, and by action of HCl, rumfolite C yielded rumfolitine B, and its diastereomer, compound 63, by the action of the HCl diphosphane, gave us ring 14C with a revised structure. But you can also synthesize ring 14C in a different fashion. Compound 62 was ketalized in methanol to ketone, then the stereoselective epoxidation, and then the cleavage of the oxide and the protection of ketone. So the ring 14C was formed also in this case. So the semisynthesis, starting from abundant caryophyllene or its oxide, provides an effective asymmetric approach towards more exotic congeners in ample quantities with confirmation or revision of their originally proposed structures. These final products can be further applied in biological activity evaluation or as reference standards in studies of metabolism of terrestrial and marine organisms. So I want to express my gratitude to Lions and the Recovery and Resilience Facility for financial support, and also all OSM members, NMR facilities, and X-ray crystallography group. Enormous assets to in this research, and also Dr. Artis Kines for DFT calculations. Thank you. I'm ready to answer your questions.
Thank you, Georgis, for this journey into natural product synthesis. So the question box is empty still. Just to raise a conversation, I can ask in the 21st slide, you had this diastereoselective oxidation with vanadyl catalyst. And can you comment that it's not straightforward to see that diastereoselectivity, as if one doesn't know exactly what the conformation of that compound 11 looks like. So alcohol is pointing up and should be kind of delivering oxygen from up, but it looks like oxygen is coming from below.
Yeah. So I can comment on this. In 19th, the group of Isidro Collado from the University of Gades studied the conformation of this allylic alcohol, and essentially it from computational studies, it's shown that this allylic alcohol indeed is stuck in the conformation in which this hexamethylene double bond points upwards. So so hence the oxidation is stereoselective. So it's the conformational issue of the starting material.
Yeah, thank you. And about that, it's very practical question. So what was the mass range of final products what you obtained? So what was that the biggest weight of the product or the smallest? So in which range you finally prepared all those many natural products?
Yeah, so essentially the roomful IJ, as you can see, it was on the gram scale. In case of room 14A and room 14C, it was indeed on the gram scale, so it's 1.5 grams for compound. So it's a tangible amount of these materials. Room 14B was a smaller one, so it was 300 milligrams. But like the linearyophyllene A was also like 100 milligrams. All of others it was on the gram scale synthesis, and maybe linear ethylene C, when we finally concluded what is the true structure of the linear ethylene C, it was under 2 grams. So tangible amounts from 2 grams to 100 milligrams.
So I guess that's the beauty of this semi-synthesis, that you have, first of all, quite available starting materials, and very, for sure, that depends on chemistry, very developed chemistry that you really produce, that you can distribute whoever wants study further the products. Okay, thank you very much. So with this, we close our highlights of organic chemistry in Latvia. Thanks for everybody who resisted until like really last presentation. And for sure, I want to express my thanks to Professor Adrian Minard, who organized this event, in the sense that were convincing us that we should step in, and then pressing us to put a nice program together. Adrian is still now traveling between places, so I don't see him on the list. But anyhow, so he was very instrumental to put this symposium together. Thanks. And for sure, I thank all the speakers who were willing to come in, to jump in and participate in quite short notice. Thank you very much. And with that, we can close and give over to European Association of Chemistry and Organic Division to organize next meetings for other countries. And also that listeners are welcome to follow those other meetings, those which are in front. And also for sure, you in EuChem webpage, you can see after also this meeting is recorded, and it will be available as other meetings from other countries. So you are all welcome to visit EuChem webpage and to check those meetings and this chemistry. Okay, with this I can close. Thank you very much. It was a joyful morning, and now it's time for lunch and for coming weekend almost, I would say, those who I don't know in person. Okay, bye. Thank you.